Hello and welcome to this lecture on complex integration. In this video, we are going to solve a problem using Cauchy residue theorem. Let's start. So this is the definition. The Cauchy residue theorem. First, we want to find the poles that we call the singular points. After finding the poles, we want to check whether it is of order 1 or more than 1. If it is of order 1, we used to say that is simple pole. We use this formula to calculate the residue. And if it is of pole with order more than 1, we used to find the residue using this formula. After finding the residues, we will use this theorem, Cauchy residue theorem, to calculate the integral over any of integral over the circle curve with for any of functions. Okay, so let's begin with the problem. So now they have given a evaluation part. So here we want to evaluate the integral over c, the function. This will be f of z. So first of all, we want to find the poles. So for that, I'm taking the denominator of the given function, and it can be written as z square z minus 2 equal to 0. Then it becomes z square equal to 0 and z minus 2 equal to 0. So this gives z equal to 0 and z equal to 2. So these are the these are the are the poles, and here if you check z, which has a power of 2, that means z2 is a pole of order 2 and z equal to 2 is of simple pole. Okay, so we find the poles. Next, they have given the region, so in which we have to check whether this pole lie inside the given curve or not. So here the given curve is mod z equal to 1 and we find the pole z equal to 0. So first we may check for the point z equal to 0. So obviously 0 will be less than 1, so z equal to 0 lies inside C, and for z equal to 2, if I find this 2 will be greater than 1, so z equal to 2 lies outside C. So if the pole lies inside it, then we will find the residue. So to find the residue for z equal to 0, of course it is a pole of order 2. That means the residue formula will be 1 by n minus 1 factorial limit z tends to a derivative power minus 1 with respect to z in n minus 1 times and z minus a whole power n f of z. Here the n value will be 2. So therefore the residue z equal to, here the a value will be also, a value will be 0. Okay, because z equal to 0. So 0 f of z equal to 1 by 1 factorial limit z tends to a d by dz, because n will be 2, so we will get d, first derivative, z minus 0 whole square f of z. So on the next step, 1 by 1 factorial become 1. So the next step will be z tends to 0, the derivative with respect to z square. F of z will be z plus 1 divided by z cube. That means we can take z square as common and z minus 2. So this z square will get cancelled. So the remaining will be d by dz of z plus 1 by z minus 2. So now we have to differentiate this term. Then we have to apply the limits. So we have a formula u by v whole dash equal to v u dash minus u v dash by v square. So let me take this u by v. So z minus 2 whole z minus 2 into z minus 1 z plus 1. So u will be here, u will be z plus 1, v will be z minus 2. Therefore on the denominator we get z minus 2 whole square, and numerator v will be z minus 2 u dash so u dash will be 1, so plus 1, then minus u will be z plus 1 and v dash will also be 1. So we get z minus 2 minus of z plus 1 divided by z minus 2 whole square, and then z minus 2 minus z minus 1 by z minus 2 whole square will give z will get cancelled, then minus 3 by z minus 2 whole square. Okay, so we have evaluated this derivative part. We get minus 3 by z minus 2 whole square. Then we apply with the limits. Now the limit z tends to 0. What we get? Minus 3 divided by z minus 2 whole square. We apply the limit z equal to 0 means we get 3 by minus 2 whole square. It will be of minus 3 by 4. So now we want to apply in the Cauchy residue theorem. That will be into our c f of z dz is equal to 2 pi I into sum of residues. Of course in this problem we have only one residue, that we call it as z, and z equal to 0 f of z. So finally into minus 3 by 4. So minus 3 pi I by 2 will be the final answer. So what the problem they asked for? Z plus 1 by z cube minus 2z square into dz will be minus 3 pi I by 2.